Okay, in this video, we're going to go over Chapter 8. This should be Chapter 8, which is an introduction to quadratic functions. And in this chapter, we start out writing the standard form. And the standard form of the parent function is often written like this, y equals x squared. But in reality, this is a better form to write it in because it now allows for more analysis. So the simplest quadratic we have is the parent function. So that goes back to this. So I've taken some of the verbiage from the textbook because I think it's good. So the power function of degree 2 in the form y equals ax squared. So what does that mean? Well, degree 2 means that the x is raised to the power of 2. And that's the simplest member of a family of functions called quadratics. Okay, you're also going to hear them called parabola. So we can use those two words interchangeably. Parabola gives more the shape, whereas quadratics refers to the power of x raised to the second power. Okay, so we've already encountered other quadratics, such as s equals 6x squared, which is the surface area of a cube, and area equals pi r squared, so that's the area of a circle. So quadratics are part of our everyday math life, if you will. So when we speak about the parent function, y equals x squared, so we're going to call it a parabola here, but remember quadratic and parabola are interchangeable. So this particular parabola, the parent parabola, is concave up. So it's concave up because a for the parent is indeed greater than 0. So this is concave up. This sketch right here is concave up. Okay. And if I drew it this way, it would be concave down. All right. And that would happen if the a was less than 0. So if I had y equals, let's just say, negative x squared, so a is negative 1, that would look like this. Okay, and it touches right here at 0, 0, even though my sketch did a poor job of doing that. Okay, the other one, y equals positive x squared or positive ax squared, that's the one we're speaking about now, concave up. Okay, so there's some other things that they speak about in terms of a parabola that you have to know. So first off, right here in this box, this gives you the standard form of a parabola. So you notice that the parent function is only, so we'll highlight this maybe, is only this piece of it. Oh, that was not effective. So let me get rid of that. Okay, it's only this piece of it. However, you can have more features of the parabola or more parts of the equation if you add this on. Okay, so that's the standard form of a parabola. Now, what makes it standard form? Well, look at your x's. If the powers go from high to low, that is standard form. Okay, so this qualifies because the power x squared is first, the power of x is second, and that's to the first power. And then if you want to really be focused on x's, you can say that c is times x to the 0 power, because anything to the 0 power is 1. So you can think about having 3 coefficients to x, a, b, and c, if that helps you to understand that process. Okay, let me get rid of that again. Okay, all right, so then that takes care of this box. Let's come over to this box. Now, what is this? Well, a parabola is kind of like our body in that it has an axis of symmetry, and on either side of the axis of symmetry, you have the identical feature. So envision the axis of symmetry as being your spinal column. How do I get an equation for that axis of symmetry? Well, first off, the axis of symmetry is a line, and that is key to remember. Since it's a line, it's going to be in the form x equals something. This is a vertical line. So if I ask you to give me the axis of symmetry, and you say 5 or 0 or whatever, without the x equals, it is wrong because you're not giving me a value for, you're not giving it to me in terms of a line. So it has to be an x equal line. Okay, how do I figure that out in terms of what the x equals? Well, for the parent function, the x equals 0 because you're on the y-axis. So that's pretty easy to figure out. However, there is a formula for it because there's a formula for everything we use in math, it seems. So x equals negative b over 2a is our formula. Where does that come from? That comes from the standard form. So back over here. So you would plug in negative b over 2a, and you would get the equation of the axis of symmetry, which divides the parabola exactly in half. Okay? So let's go on to the next page as I have more items to discuss in terms of the specifics of a parabola. Okay, so far we have discussed this box and this box. So now let's look at this box right here. So the focus is not always discussed when it comes to parabolas, but it is discussed in our textbook, and I think it's worthy of discussion. So the focus is located absolute value, which means no sign, not positive nor negative, of 1/4 and then times a in the denominator. So remember, the a comes from the standard form right here, and the focus is always located inside the arms of the parabola. So in this situation, there it is. So it's either 1/4a absolute value units above or below the vertex. Okay, so that brings us to vertex. What is the vertex? Well, notice your axis of symmetry, x value, is the x value for your vertex. Then the y value is your original function, that's the function of the parabola, evaluated at the x value that identified the axis of symmetry. Okay, so you would just plug in the x value to your original standard form function, and you would get the y value. That vertex is either the max or the min of your parabola. Okay, and then that takes care of that box. So now the concavity of the parent function is concave up throughout its domain. So we talked about that in the first page. And then the last box here says, remember the quadratic formula used to find the roots. And the roots are where the function crossed the x-axis of the parabola. This is the quadratic formula. Okay, so the a, b's, and c's all still relate back to the standard form of the parabola. All right, this formula you want to use carefully. I'm going to probably always provide it for you, but the key thing is it's negative b plus and minus the square root of b squared minus 4ac all over 2a. Okay, so both the negative b and the radical part are divided by 2a. So that's an important thing to keep in mind when you're doing this. Okay, let's go on to the next page. Okay, on the top of this page, they start talking about the parabola and the focus. So it says a focal point, so that's where the focus is located, merits its name. A three-dimensional parabolic bowl, so think about a parabola in a 3D mode, has vertical cross-sections that are all the same parabola. If the bowl is built of a reflective material, the parabolic shape will concentrate parallel rays from the sun or a satellite TV channel at a focal point. Okay, so here is a diagram that shows the focal point with sound coming in or going out for that matter. So this property is used to focus the sun's rays to construct primitive cooking devices. So that's kind of a cool thing. So if you think about this being a cooking bowl and the sun's rays are coming in this way, as it bounces off the parabola, all the energy will be focused at that dot. Remember where that dot is located. 1/4a absolute value distance from the vertex. So the vertex would be right about here. And you can see the focus is inside the arms of the parabola. So that is where all the sun's activity or rays are concentrated. So they talked about, let's work on an example of this. It says designing a cooking device. In developing countries such as Burkina Faso, solar parabolic cooking devices provide a cheap way to cook food and pasteurize water. The cooking device can be made any size and can even be constructed of hardboard and aluminum foil. Okay, so it kind of reminds me of the cooking boxes that the Girl Scouts make that are lined with aluminum foil. If a large parabolic cooking device is built that is 4 feet wide and 1 foot deep, where should the cooking pot be centered for maximum efficiency? So the answer is going to be, you're going to center that cooking pot at the focus. And where is that located? 1 over 4a, absolute value, from the vertex. Okay, so then down below they go through that example. So let me do that on the next page. So here the authors go through the solution for us, and you can see it says the cooking pot should be placed at the focal point of the parabola where the sun's rays are concentrated. Remember again, the sun's rays are coming in from this direction. And if you think about the vertex as being at 0, 0, and if your equation is in the form y equals ax squared, you can use that to find the focal point. To find the value of a, we need the coordinates of a point on the parabolic cross section. Since the cooker is 4 feet wide, if we move 2 feet to the right of the cooker's base and 1 inch up, it'll be at the point 2,1, which lies on the rim of the cross section. Okay, so here is a point that lies on the rim of the cross section. So let's see what they're doing then. Given those numbers, they can figure out, okay, the general equation is y equals ax squared. I have 2 values to work with, so this point 2,1 is key. Now, how do they get that? Well, if your shape is 4 feet wide, remember that the axis of symmetry divides your parabola exactly in half. Therefore, you have 2 feet on each side. Okay? So that's where the 2 comes from. So they've done that, and if you plug in for your values, what's going to happen is that you're going to be able to calculate where your focus is, and then you can measure where that's going to be. So that's going to be 1/4 of a foot from your vertex, which is right there. So that's how you would locate the focus. Now, just to be clear how they got the 1, because I think I've only addressed how they got the 2. So they told us that the shape was 1 foot deep. So therefore, you can figure out that a point on that bowl is going to be 2, 1. And then those are the 2 values you use, because now your goal is to figure out what A is. So if A is 1/4, then that's going to get us closer to knowing where to put the pot. So in just continuing, so I have 1 over 4A is the focus location. I have now figured out what A is, so let's continue. 1 over 4, 1 over 4, and then absolute value. The 4's cancel, that becomes 1. So you should put your pot 1 foot above. So above that focus, so above the vertex. So that's how you solve these kind of problems. So again, to summarize, we worked out that your pot is going to be at 2, 1. We use the 2, 1, which are the x and y values, to figure out the a. Once you have the a in your original parent function, you can then figure out the location of your focus. It's always going to be within the arms of the parabola. Since this parabola faces arms head up, it's concave up, that focus is 1 foot above the bottom. So just a quick summary of the properties of a quadratic function. So we haven't talked about the vertical intercept yet. So the vertical intercept is also called the y-intercept. So it's where the parabola crosses the y-intercept. Okay, and you can get that y value by plugging in a 0 for x, because this point right here is 0, 0. Okay, so that's the vertical intercept, or aka the y-intercept. Okay, the horizontal intercepts are also called the roots. They're right here and right here. Okay, those roots can be determined by using your quadratic function. Right down there. Okay, then we have talked a lot about the focal point. We don't have it in here. However, we do know it's going to be somewhere around here because it's going to be inside the arms of the parabola. If I knew what the A is, I could calculate it. Okay, so then on the next page, we're going to talk about the 3 possible cases for the roots of a parabola. So let's do that next. Okay, so here are some examples of the possible number of roots. Remember, the roots are where the parabola crosses the x-axis. So here's case 1. Okay, case 1, and we're going to be referring constantly to this quadratic formula. If you take the information that's underneath the radical, okay, that's called the discriminant, that's going to give you information about your roots. So if you calculate the discriminant, which is just b squared minus 4ac, all those letters once again are coming from your standard form, you can see that if that number underneath the radical, if it is less than 0, so if it's negative, then you have a situation where you have no intercepts. So there's no x-intercepts. So you can see that your parabola is floating above the x-axis, so it's never, ever going to cross it. Okay, so that's scenario 1. Okay, scenario 2 is if that discriminant equals 0. If that equals 0, then you have what appears to be just one root. Technically, it's a double root, so it's plus and minus the same number. 0 is it's whatever negative b is, plus and minus 0. So it's called a double root, but it'll appear as if it's one single place. So what's happening is the parabola comes up to the x-axis and then pings right off. So you have one root. Okay, that's scenario 2. Scenario 3 is where the b squared minus 4ac, which is once again the discriminant, is greater than 0. And if that's the case, you get what they call two real roots. So in terms of roots, you always have to have 2 roots because it's a quadratic. So, that seems odd. So in this situation, I don't see any roots, but you have no real roots, so that's what you can see, but you do have 2 imaginary roots. Okay, so we'll go over that at some other time. So here you have what they call a double root, and it's all located at one place. And here you have 2 real roots. Okay, so let's continue talking about our quadratic on the next page. Okay, this little chart is a nice summary of what we've gone over so far. Here is your standard form. We have the word parabola. We know that the parabola is symmetric, which means it's the same on either side of the vertical axis of symmetry, and that's going to be an x equal line. It has a minimum if it's concave up. So if it's concave up, you have a minimum right there at that vertex. You have a maximum if it's concave down. And those points of the max and min are called the vertex. Okay, it has one vertical intercept, okay, but may have 0, 1, or 2 horizontal intercepts. So the vertical intercept is the y-intercept. The horizontal intercepts are the x-intercepts. And the focal point is 1 over 4a, absolute value, units above the minimum or below the maximum. Okay, the value, absolute value of 1 over 4a is called the focal length. So that's a nice little summary. Okay, so the next problem, we're starting to do some applications of these quadratics. So if it says, what is the maximum rectangular area you can enclose within a fixed perimeter of 24 meters? What are the dimensions of the rectangle with the maximum area? So if you have a rectangle, so the rectangle region has a length of L and a width of W, then if you can think about, so here's your, okay, here is your rectangle, length, width, so the perimeter would be 2L plus 2W. Okay, so then what are they doing here? They are writing the perimeter in terms, the width in terms of the length, so that they only have one variable. So let's continue this on the next page, but that's our basic setup, and we'll continue it in just a sec. Okay, so let's resume our discussion of this maximizing area problem, because it's kind of a neat problem, because you take a rectangle, but when you are trying to maximize the area, that area can be represented as a quadratic, and this is why. If they tell you have a fixed perimeter of 24 meters, okay, so that's 24 meters. Here is my garden to begin with. Here is the area. So the total area is going to be length times width, but my lengths and my widths all add up to 24. So if that's the case, what you can do is you can write 2L plus 2W equals 24. Divide all three terms by 2. That gives you length plus W equals 12. Then you're going to write W in terms of L. And the reason why you're going to do that is you want to have only one variable. So this is what happens. So now down here, we're trying to figure out this area. And we use the information about the perimeter to express the area in terms of length and W, but we are writing W as 12 minus L for this reason. So now look what happens. Find the area, length times width, and you get this. Okay, that is a quadratic expression. So if you're going to do that and you want to figure out where the vertex is, so what is that? Well, let's see. If you look, you can figure out your, your y, or your f of x, we'll say, equals negative L squared, it's going to be a max, it's going to be downward facing parabola, plus 12L plus 0. So what is your A in this situation? Well, your A is negative 1, and your B is 12, and your C is 0. So what is your vertex? Your vertex is your X and your Y. So let's think about that for a second. So as we're thinking about that, I want you to look at this parabolic shape. That is your area function. So if we just analyze the graph, we could figure out where the max would be. So, but we are able to do more than just analyze the graph, because we have an equation for the vertex. And that equation is, so the vertex equals negative b over 2a, that's the x part of it. Then once you have the x, evaluate that function at negative b over 2a. That will give you our y value, and that's how we're going to do it. So let's see how they explain the solution. Figure 8.8, yes, that's the one I just referred to, shows a graph of area, and we are seeing that, let's see, so the parabola is concave down. Yes, we knew that because the leading coefficient is negative. From the table in the graph, it appears that the vertex of the parabola is at 6, 36. Okay, so right here on the table, that's the highest part, and that is consistent with what we're seeing in the graph. So we could then figure out that that would have been our negative b over 2a would have gotten us 6. Okay, and the f of 6 is indeed 36. So that all works out. So what we have discovered by using our equation for the vertex, we have discovered that when the rectangle has a maximum area, that happens when the length equals the width, or in other words, when the rectangle is a square. So how did I do that? Well, I figured out the L was the length, so I'm plugged in the 6 for the L. That gives me the width of 6. So if you have a freestanding garden, the maximum area always results when you have a square plot. Okay, so the length is going to equal the width. So you can answer many questions with this problem. You can figure out what is the maximum area. You can figure out the L, which we did, or you can figure out the dimensions, which are 6 by 6. Okay, so go through this problem. It's a good one. It really shows how you can apply quadratics to a practical problem of maximizing garden area. Okay, so this is another classic problem where you have a trajectory of a parabola and they ask you questions about it. So here they want us to estimate the height from which the projectile was launched and estimate when the projectile hits the ground. So the height from which it's launched is where the time is 0, and that is the y-intercept. So that's interesting. So this question A is asking us about the y-intercept. What is question B asking us? Well, where it hits the ground. So if we were to continue this path, we can kind of figure that out. And question B is asking us for a root. So this question right here is looking for a root. Okay, a special root, the second root, because the first root will be somewhere over here in negative time, which does not make any sense. So we're looking for the second root. So what we had to do in this problem is to use our calculator and plug in certain x and y values that you can get from this table. And then there's a function under stats which lets you predict or estimate a parabolic function. So they have done all this. We'll do this together, but they got this equation. So let's say you have this equation. How do you work out what you need? Well, first off, the y-intercept is the c value. So c, right, in the standard form, is your y-intercept. That's the height from which this has been launched. Then how do you get your roots? You get your roots by using the quadratic formula. So you can read through this, but we end up realizing that a projectile hits the ground at 6.2 seconds. So we can see this is going to be 6.2 seconds. So if you use the quadratic formula and you use the A, B's, and C's that they got from the stats analysis, then you will get 6.2 and you'll get a negative number. That negative number is not germane to our discussion. Okay, the negative time doesn't exist, so you only focus on the second x-intercept for the answer for this problem. So let's move on to the next problem. Okay, so in this on this page we have some practice problems. So I would recommend that you do these and make sure that you are understanding the topics that they're covering. So the first one says find the coordinates of the vertex and the focal point for each quadratic function. So I'm reminding you, you get your vertex this way and you get the focal point that way. And remember, it's always going to be inside the arms of your vertex. They also say specify whether the vertex is a maximum or a minimum. So if the leading coefficient, so right here, this is negative. If the leading coefficient is negative, then you're going to be concave down. If your leading coefficient is positive, like it is in this situation, for C, then you're going to be concave up, and it'll be a minimum. Okay, maximum for concave down, minimum for concave up. So you should be able to go through those problems for number 1 without a whole lot of work on your part. Okay, coming down to number 2. Number 2 is very similar to the cooking example that we had, where you had to figure out where the focal point is. And this is kind of interesting because it makes you think about how outdoor concert areas are designed. So try to go through this one as well. And then the problems down below for number 3, evaluate each of the following quadratic functions at various x values. So those values they've given you of 2, -2, 0, and z are the values for the independent variable, which is the x, the w, the t, and the r's and the s's in the problems below. So try to do that. You may certainly use your calculator to do all of this, and you should come to class with many questions about this. So let's go on to the next page in just a sec. Okay, so just to clarify, these were questions 3, where you're going to substitute in your values here into the values on the right side of each equation. Those are your independent variables. So then down below, you have these scenarios 1 through 5, and you're going to match them. You're going to discuss each of them for the 4 graphs below. So concave up or down, maximum or minimum, the equation of the axis of symmetry. Remember, that's an x equals equation. The estimated coordinates of the vertex. So that's your negative b over 2a, and then the function evaluated at negative b over 2a. And the estimated coordinates of the horizontal, so that's quadratic formula, and vertical, that's if you plug 0 in and see where the y-intercept is. So for these, you can do all of these visually. I wouldn't try to make a formula by plugging things in your calculator. You can just do a visible analysis and get the correct answers for each of those parabolas. Okay, this next section, 8.2, they're calling visualizing quadratics, but really it's really transformations to quadratics. And what they're doing is they're giving you the quadratic in what they call vertex form. So we're going to go through all the different transformations or changes you can make to a parabola. And the best way to view those changes is if you take it from standard form and you put it into vertex form. So let's go through some of the changes now. So if your basic equation of a very parent function type parabola is ax squared, what a is has an impact on how your parabola looks. So if a is a number that is, well, these are all positive numbers, by the way. If a is a number that is less than 1, you have what they call a vertical compression. So you think about pushing down on your parabola. And when you push down on your parabola, the arms go out further, and that is considered a vertical compression. So that's a compression. And they're telling you right here, what a compression is. A vertical stretch is if you have numbers for a that are greater than 1. So they're putting that out to you right here. And so if you have 5 or 2, that is a vertical stretch. So think about taking your parabola and stretching it up. So you make it tall and slender for vertical stretches, and you make it fat and squat for vertical compressions. So that's what we want to understand in this first transformation, stretching and compressing vertically. Now the next transformation is called a reflection. So we're reflecting across the horizontal axis. So if you have y equals 5x squared, this is what your parabola looks like. And if you have y equals negative 5x squared, look what happens. You are flipping over the x-axis. And that's what they're showing you down here. Okay, so here are negative A values, and here above are positive A values, and you can see the impact it has on your parabola. Okay, let's go on to example 1. Okay, in this example, they're asking you to describe the relationship between pairs of quadratics. So what you can see is if this is your original quadratic right there, it is flipped over the x-axis. Okay, if you are comparing the purple line to the red, so we're going to call that the red one, you can see that's just a flip over the axis. If instead you are comparing the red with, let's make it kind of a brownish color, with this brownish green, so the red and the green, you have vertically compressed the green to get the green. You have vertically stretched to get the red. And you can go through the same exercise with this next graph B. So you want to know about these features. So these are transformations, 2 of them, vertical stretches and compressions, and flips over or reflections across the x-axis. Okay, the reflection is when you have a negative leading coefficient. That puts you on the other side of the x-axis. Okay, so let's go on to the next page. Okay, on this page we are doing our third transformation, and this is shifting vertically and horizontally. So first off, shifting vertically, you're moving up and down along the y-axis. So if you add a C, that is going to be a shift up or down along the y-axis. So if you are taking a parabola, so this is graph B, and if you wanted to shift it up, you would add 2, so that would be a shift up right here. If you want to shift it down from where it currently is, you would subtract 2. So that's vertical and vertical shifts up and down. All right, so they've discussed that here. They give you another example in example 2. So let's go on to the next page. So here we're doing another transformation, and this is shifting a graph horizontally, so east to west as opposed to north and south when we did vertically. So when you shift horizontally, you are shifting in next to the x variable. So they give you 2 examples here and here, but I think that these are the most informative ones. So first off, they are writing your equation in this form. So what are you noticing? Here the black, so the black one right here is your standard parabola. So say that is just y equals 3x squared. You are going through the origin. You've neither shifted left or right off of that y-axis. If you shift right, look what happens. You have a negative operation. So shifting along the x-axis is always a little goofy. If you look at 3 times x minus 2 squared, you would think you're shifting to the negative direction, but you are not. X's are goofy. If it's x minus 2, you have shifted to the right, the positive direction. If it's x plus 2, you are shifting to the left in the negative direction. So you've got to remember that x shifts are always goofy. They're opposite what you would think, as opposed to vertical shifts. If you were originally here and you shift up, that would be adding. If you shift down, that would be subtracting, and those are the C values. These values for the horizontal are in next to the x, so they're inside a parenthesis that's being squared. All right, so you have to recognize the difference between the horizontal and vertical shifts, and you've got to recognize those patterns of shifting. So always think opposite for the horizontal shifts. Okay, so in this page, I have cut off the rest of this example, but it does take you through looking for vertical and horizontal shifts, and also reflections over the x-axis and vertical stretches and vertical compressions. So make sure you're comfortable with that. This is a very nice summary of horizontal and vertical shifts. On the previous pages, you had a summary of the compressions, the vertical compression, a vertical stretch, and the reflection over the x-axis. So you need to know all 5 of those changes. And then on the next slide, we'll talk about the vertex form of a parabola and how that's an important thing and what it tells us. Okay, so here is your vertex form. Now, the vertex form gives us some very good information. Just like standard form gives us some good information. So let's just refresh on standard form. So standard form would be, and these are both of parabolas, ax squared plus bx plus c. Okay, what kinds of things can we do with that? Well, the a, b's, and c's can give us things like the vertex, negative b over 2a, and then the function evaluated at negative b over 2a. That can give us also the axis of symmetry. And what else can it tell us? Well, it can tell us if you have a reflection over the x-axis. So there are a lot of good pieces that it can tell us. It can also tell us the y-intercept because that is just your c value. Okay, so then they bring us to the vertex form. So this is the vertex form. It can also tell you some good things. So the a is still present, and so that can tell you whether you have a vertical stretch or vertical compression, and whether it's positive or negative will tell you if you're shifting over the x-axis. The h and the k are your vertex, so you don't have to say negative b over 2a. You can just read it. This is the standard form, so that means if you just directly read h comma k, that is your vertex, and that's an important thing to notice. Okay, so the vertex form is also called the AHK form. So be able to spot that both ways. Okay, let's move on to our next page. And they're never asking you, by the way, to get it into that form. They will give it to you in that form. Okay, so for this lesson, you just have to recognize the form and be able to read it. Now, it does get a little bit tricky sometimes because you've got to recognize that you have to have a negative in between the x and the h if you're going to read this directly. So look up here for a sec. Do you see how you have a positive there? So that means that your h value would be the negative 2. And you see how you have a negative here? So that means that your k value would be a negative 4, which is consistent with the vertex right there. As opposed to this, which matches our form directly, and I can read 2 comma 5 right there and get that vertex. So you should be able to say, okay, in both cases I have vertical stretches because I have my a's of 3. In the second case, I have flipped over the x-axis. What else is going on here? In this situation, I have plus 2 inside next to the h. So that means I've shifted my graph to the left 2. Remember how it's goofy inside? As opposed to the x minus 2 in this case, where I have shifted it to the right. The negative 4 in the graph of y1 tells me that I have shifted vertically down 4, and the positive 5 in the graph for y2 tells me I've shifted up 5. So you should be able to look at these equations in vertex form, because that's how they're given to you, and be able to say what your parabola should look like. In the first case, for the y1, I see that I have a parabola that is concave up, and therefore the vertex would give me a minimum. And in the second scenario, I see a parabola that's concave down, and that vertex will give me a maximum. We can also discuss the focal point in both of these situations. They're both going to be inside the arms of the parabola. So all of this is what should be accessible to you in terms of your discussion of parabolas. Okay, so on the last page of this 8.2 section, they talk about domain and range. So a couple of things about domain and range. If you have a parabola that looks like this, the domain and range are going to be the following. Okay, first off, domain for all parabolas. It's always going to be all real numbers, which you can write like this, or you can write it in interval notation, negative infinity to positive infinity. So every x is included in the domain. That's what that means. Okay, so that is an easy thing to understand and an easy value to get for every single parabola. Okay, the range is determined by the direction in which the parabola is going and also by the k. So that's the y value of the vertex. So for example, if I had something like this and say my k was at, say that my hk was at 0, 4. Clearly my domain has not been impacted. That's why it's always all real numbers. But my range would be definitely impacted. So where does my range happen? You always go from low to high. So I would write it that my parabola's range here, it starts at negative infinity, and then it goes up to a high of 4. So negative infinity to k in this situation. Okay, that's a downward facing parabola. What if I just flip this guy over and I made that vertex 0, negative 4? Starting low, my range would be negative 4 to infinity or k to infinity. So this clarifies that pretty much. So be able to understand that for this section as well. Okay, so if you draw them out for yourself, you can kind of understand it. So make sure that you understand that as the arms go out, they're not really going straight up vertically. They're going out, and that's why they're including all x values in the domain. The range is restricted and impacted, I should say, by the a value. If it's positive, it's opening up. If it's negative, it's opening down. And also the y of your vertex. So that completes sections 1 and 2. This is all very important information. So go back and make sure that you've gone through the examples and that you understand the material.